Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are looking at diffraction, and if you look at the diffraction of waves, you get water waves where we get diffraction, and you get light waves where there is diffraction. And we will be looking at the diffraction of light waves today. And the definition of diffraction, according to the Department of Education, the ability of a wave to bend or spread out in wave fronts as they pass through a small aperture opening or around a sharp edge, point, corner, or barrier. Now, that is a definition of diffraction. And when light goes through a narrow slit or a narrow opening, what happens is that it bends. So here we have an example in front of us of an applet that shows the what happens when light goes through a narrow slit. We have red light going through a narrow slit, and when it goes through a narrow slit, we see that the light doesn't go straight, but we see a spreading out of the light. And when the light spreads out, it makes a pattern, as is shown in this picture at the bottom. And furthermore, we see a graph that shows the intensity of the light. When we look at the central band, when the light goes through, most of the light goes straight through, and we see this curve here showing where most of the light is. And then we see a point of zero disturbance that is here, where we see it as black on the screen. And then we see that there's again, the graph goes up where we see there's some light here, and then it gets dark again, and then it gets light again. So we see alternating bright and dark bands according to the pattern here, and this graph depicts the intensity of the light when light falls onto the screen. Now, we get a difference between when single light falls onto a screen and when double light falls onto the screen. So, if we take this further, we will see a picture of where single light falls onto a screen and where double light falls onto the screen. Importantly, I just want to mention that these Java applets that I have, they are very beautiful, and they can be sourced at this website that I've placed here on the side. It's an excellent tool for understanding physics. Now, going a little further, we see that there's a difference when there's a single slit and when there's a double slit. When light goes through a single slit, we see the pattern as shown here on the left, where we have a broad band, central broad band in the center. Then we get alternating light and dark bands as you move away from the center. But if you use a double slit, we see that we don't have a central broad band. We have an equal with alternating dark and bright bands. The bright bands are areas of constructive interference, areas where light intensifies, and then we get areas of destructive interference where the crest of one wave meets a trough of another wave, and we get dark bands. So it's important to realize that the single slit has alternating bright and dark bands, and a double slit has equal bright and dark bands, as seen clearly in these two diagrams. Another important point to remember is that if we compare, for example, red light to blue light, we see that the red light, when it falls on the screen, forms a broader central bright band compared to the blue light. So if we compare the pattern formed by red light and blue light, we see that the red light has a wider pattern. So we can conclude from this that red light bends more, diffracts more than blue light. So as you move from red towards violet in the spectrum, you get red, orange, yellow, green, blue, indigo, violet. Then what we see is that the central band gets smaller. So as the wavelength moves from red, which is the greatest, to blue, which is the smallest, we see that the central band decreases in width. And this can be seen clearly here as well from the double slit and the single slit, where the red bands are wider than the blue bands. Now, what is important here for exam preparation is that they may ask you what is the width of the central broadband. Now, I've drawn a diagram here where we see that if you look at it from the top, where light is coming from left to right, when light passes through the slit, And it's important to realize that um, the slit has a symbol which we use in an equation, and in this case we see that the slit is described as A. Then according to this equation, we see that the important equation that we have to know is this equation that says sine theta is equals to m lambda over A. Then the slit has the symbol A. The width of the slit is A, and then so A is the width of the slit. Width. Just fix that up properly. The width of the slit is A, and then you've got M, which got to do with the dark band. Now, what we mean by dark band, we're talking about whether the band is the first band or the second band. And then we got lambda, which is the wavelength of the light. So in this case, we see that light goes the central band where most of the light comes through, most of it goes straight through, and that's where we get our bright band. Then this here will be our first dark band. And then this will be our second dark band. So if we wanted to know what is the angle of diffraction from to the second dark band, then we will look at from the slit to there. Now what I did here is that if you look at it from the top, we can see that if you draw a line directly straight through where the line goes, right up to the beginning of the first dark band, we can form this triangle. And this triangle is a right angle triangle, and we can use trigonometry ratios to find how wide the central bright band is. As we saw in the earlier example, we saw that the red band is wider than the blue band. So they may ask you a question in the exam, and they'll give you, for example, they'll say the wavelength of light that falls onto the screen of red light is 650 nanometers, and the angle of diffraction to the first dark band is 15 degrees, and they'll say calculate the width of the slit of this particular case. So then we'll use this equation, sine theta is equals to m lambda over A, and then we'll say sine, and our angle theta is what we want to find. So the angle of theta is given as 15 degrees, and m, in this case, we want to find, we're talking about diffraction to the first dark band. In this case, it's there, so it's 1. And lambda will be 650 nanometers, which becomes 650 times 10 to the nanometers is minus 9. And then if you divide that by A is the width of the slit. And if you have to work this out, if you cross multiply, A is equals to 650 multiplied by 10 to the power minus 9 all over sine of 15 degrees. And this is simple calculator work now. And then if you work that out, we see that we can calculate our answer. So let me just calculate that for you. And when we work that out, we see that we get 2,7 times 10 to the minus 6 meters. So that will be the width of the slit. So if you look at it, the width of the slit will be 2,7 times 10 to the minus 6 meters. So that is a summary of a simple question on diffraction that you could expect in an exam. Just to summarize quickly, you should know that the definition is important. What is the definition for diffraction? And then going further, we see that when light goes through a narrow slit, you can get light going through single slit, where we get a central broad band with alternating dark and light bands. The bright band is because of constructive interference, and the dark band is because of destructive interference. And the dark band will be destructive interference. And then we see that there's a difference in the patterns that are formed. We see that if there's a single slit, we get a central band with alternating dark and bright bands. And if we have a double slit, the pattern is different, where we get equal width of alternating bright and dark bands. And then another question that could be asked is, if they give you a certain information like the wavelength and the angle, then we can use that to calculate the width of the slit. And we can also say that as the wavelength changes from red light to blue light, and as the wavelength decreases, the width of the central band decreases. And if we even look at this here, we can see that sine theta, in terms of the angle, one more aspect that we should remember, if you look at sine theta is inversely proportional to A. That means as the width of the slit decreases, the angle will increases. So the narrower the slit, the greater the diffraction. So that is a summary of the section, and good luck for the exam.